We can see for the 2 3 minutes more. If nobody joins, then we can start. So I think we can start now. So what we have seen previous week. So we quickly recap what we have seen. So we have seen mostly about the strengthening mechanisms. Okay, there are various ways we can do strengthening of any given material. So first one is the grain boundary strengthening. So if we see any material, if the grains are become coarser, uh, its strength will be, its hardness and strength will be less compared to the ones we are having the grains of finer. Okay. One of the way to increase the strength of the material is to reduce the size of the grains. Second is the increasing the second is the cold working. We can do the cold working to improve its increase the dislocations density and create more distortions in the microstructure. So which will ultimately results in increasing its strength. Third, martensite strengthening. So martensite is a phase which is having the which forms when we quench it at much when we cooling it at much faster rate, so that we are avoiding touching the nose curve. So that time we can see the martensitic phase. So if we introduce this martensitic phase in a certain proportion into the microstructure, it will strength will be increases. And strain hardening. Strain hardening is also one. It is nothing but like a cold working, cold working similar to that. And fiber strengthening. Suppose in case of fiber reinforced polymers and so on, there we can, in metal matrix we can add a fibers to increase its strength. Solid solution strengthening and strain aging. So you can see some of the strengthening mechanisms here. These are the primarily what is the strength way, different way of strengthening uh, we can achieve here. Okay. So yeah. So we have seen what is the how the dislocations will how the dislocations generate and how the dislocations will move, and we have seen how the grain boundary strengthening happens. So first one is the solid solution strengthening. Here we will replace the a single atom with another atom which are having the bigger size or smaller size than the parent material matrix. Okay, suppose in the case of iron, if I add another element which is having a much larger size, so it will generate the lot of internal stresses into the metal matrix. So if the stresses are this dislocation, this crystal structure very much deformed, and stresses are there, so which will act as a barrier to dislocations to move further, so that will increases its strength. So this is the solid solution strengthening. So we have seen different elements how we can increase its strengthening. So the second is the precipitation strengthening. This we can see mostly in the case of aluminum alloys or any materials. So here we will put a one entire one precipitating element like any ceramic elements are like that. Ceramic reinforced metal matrix, or aluminum copper case, we can by aging we can do the precipitations forming in the metal matrix. So these precipitations are much harder press and also brittle also. So we don't want entire this matrix to be this precipitation phase, because it is because of its brittleness it will not withstand it will not give much more toughness. So we want to disperse in the metal matrix, so that when the dislocation moving, this will act as a obstruct to dislocations to move. Okay, so this is how this precipitation will increase its strength by offering more amount of the more obstacles to moving of the dislocations. Okay, so how we can produce the dislocation, that is also we have seen. Next is the cold working. To the once the we did the cold working, the plastic deformation happens, and highly the microstructure will be deformed more, and dislocations will be uh, entangled with one another during the cold working. Hence dislocations motion become more difficult. Okay, so if you want to reduce the if you do the heat treatment, the recrystallization will be um, happens, and this is the what are the benefits we got from this cold working will be reduces. Okay. And strain hardening. So it is the strain hardening is nothing but so we will apply the certain amount of the force, apply the, so once it reaches to the maximum here point, this strain maximum point, then we will cool it down, and then we will do the heat treatment, heating. Then once it crystallization done, again we will do the straining. So we continually repeat that, so that the finally the material strength will be increases. Okay. and this is also rolling, also one of the cold working operation. Okay. And this stuff, these are all we have seen in previous class. Okay. So now I will go to today talk. Today what we are going to see. So today we will talk about the heat treatment processes. Okay. So what is the different heat treatment processes are available? So generally, once we talk about the heat treatment, we will broadly classify them. In general, there are the three different heat treatment processes are there. So first is the, so if, what is heat treatment is that, so in general term, heat treatment is that we will heat the material above recrystallization temperature and we will hold it for some time, and at what rate we are cooling it makes affects the its microstructure. So in simple words, changing of the metal microstructure by heating it and cooling it at different rates and at different temperatures. Okay. So if I have a, in case of iron, so above 750 degrees or like that, so we can see the gamma phase here will be present, gamma phase. Okay. So below that it will be paralytic, or paralytic phase will be present. So if I want to change the microstructure of this final my material, first I will heat it to around 900 degrees or like that. So that entire my microstructure will be converted into gamma phase. Then I will hold it for some time. Then which cooling rate I am following defines the which process, which heat treatment process it is. Okay. If I am doing the furnace cooling, it will be the annealing, because it is the very slow cooling rate. And if I do the normal cooling, that is air cooling, it is called as a normalization. And if I do the what if I dip it the sample into the water, then it will be called as a quenching. Okay. So how the microstructure will affect because of that is the. Mm, yeah. See here, if I do the furnace cooling, so it will be the slower cooling rate, so we can get the coarser grains. But if I do the normal cooling, because of the slow relatively faster cooling compared to the annealing, I will get the finer grains, but it is in the paralytic form. Okay, here also it is in paralytic form only. But if I do the quenching, water quenching, the it will not touch this nose at all. What is this nose representing? It is representing the starting point of uh, paralytic phase formation. Okay, so above it gamma phase, that is FCC, paralytic is the BCC. So conversion start not immediately, it will start, it will start at here and it will end at here. Okay, so here it means 99% of the metal microstructure is converted into paralytic phase. So if I do the water cooling, it is not even touching the starting point of this conversion of paralyte, so it will directly cool down. It is nothing but a we can call it as a retained austenitic phase. Retained austenitic phase means same thing, but it is actually not stable phase. But because of the faster cooling, it was a FCC phase still retained into the room temperature. So this phase we call it as a martensitic phase. Martensitic phase generally having the very high hardness. Okay. So this is the three different general processes of heat treatment. So we will discuss much more into these processes while we directly going into the problem solving case. Okay, while problem solving itself, we will discuss more into it. Okay, so here is the some of the questions from this annealing, heat treatment, and annealing, normalizing, and quenching. Okay, so which of the following heat treatment process produces the softened microstructure in hyperreductide steel? Okay, so softer microstructure, nothing but a coarser grains. So coarser grains means we are having a much more ductility high, hardness will be less. Okay, so quenching generally produces the based on the alloys also, because if they see in quenching, if the based on the alloy composition, it may form multistatic phase or paralytic phase. Generally it will produces the very hard phase. Okay, either multistatic phase, or if it is from the paralytic phase, it will be the very finer structure with high high hardness. Okay, second is that normalizing will produces the relative, compared to quenching, it will produces the softer phase, but it is compared to annealing, it is the much more harder phase only. So arch tampering, no, arch tampering also it will forms the benetic phase, so that is also not the case. So answer will be the annealing only, which will produces the much more uh, ductile phase. Okay. So here is the so here is the what is the three different processes. Okay, so answer will be the annealing. So here in annealing, steel heated above the critical temperature and cooled very slowly inside the furnace. Okay, furnace cooling, allowing the formation of the coarser perlite. Coarser perlite has the lower hardness, higher ductility compared to the finer perlite. That is the normalization. Metastatic phase forms when we do the quenching operation. So therefore annealing produces the softer structure. Okay, next question. Normalization differs from the annealing primarily in how the normalization differs in annealing. So how we can get the difference is that first, both two processes we will follow the similar trend. This is the generally what we so here x-axis will be the time. Okay, time, here y-axis will be the temperature. Okay, so we will both normalizing and annealing, we will follow the similar heating rate and similar holding time. But in normal case, we will do only difference is the cooling rate. So in case of normalizing, it will be the much faster cooling, and this will be the normalizing, and this will be the annealing. Annealing will be the furnace cooling, so it will be the much more slower cooling. Normalizing is the we are doing it to air environment, so it will be the bit faster cooling rate. So only difference will be the here cooling rate only. Heating temperature, no, because in both cases we can follow the similar procedure. It doesn't affect. Cooling rate is the one. Carbon content, no, because carbon content only affects the how much of hardness and so on, but it does not affects um, the way process it will be saying. Holding time, no, holding time also doesn't affect. So only cooling rate is the what differs the normalizing, annealing, even though quenching also in certain aspect. Okay. Both process heat steel above critical temperatures. In annealing, cooling is slow, furnace cooling. In normalizing, the cooling is in still air, faster than the furnace cooling. Okay, but it is much slower than the quenching. Quenching is we done it some liquid like water or any other oils or a brine solution or other other way of faster cooling. Okay. So the cooling normalizes results in the finer perlite. So if I finer normalization, we will get the finer perlite, and if we do the faster slower cooling, it will be forms the coarser perlite. Okay. Next, martensitic form during the quenching occurs due to. Okay. So martensitic forms during the quenching occur due to. Why martensitic forms during the quenching? Because of the diffuseless transformation. Uh, yes, we can say like diffusionless transformation is the one of the property of martensitic phase, but that is doesn't means that it is martensitic phase forming due to diffusion. No, martensitic means diffusion-less transformation. Here option is diffusion control transformation. No, because diffusion control transformations are normalizing and annealing. There we can control the how the paralytic phase forming and so on. Where we getting this kind of diffusion is that, so you can see here. Mm, yeah. So once the phase is forming, so this gamma phase will be in case of if we are having steel, their carbon percentage less than 0.8 percentage. So here we can see like alpha phase first forming at the grain boundaries, and this carbon will be diffusing into the uh, gamma phase, and it will again convert into the paralytic form inside and surrounding by the alpha phase. So it is the diffusion happening in controlled way. If it is a diffusioning happening much slow, like in case of annealing, it will be takes for much longer time. In case of normalizing, it will be very short duration, but diffusion is controlled. But if in case of martensitic formation, there is no such diffusion will be takes place. So first option is no. Next is the slower cooling. No, definitely not. Slower cooling means it is the annealing. It will comes under annealing. Definitely not. Next is the shear transformation without diffusion. Yes, because without diffusion it is happening, so it will be the shear transformation. Okay. Uh, diffusionless transformation. Okay. Formation of the cementate. No. Formation of the cementate happens uh, in related to the amount of the carbon percentage. Okay. So this is also not. So answer will be the C. Okay. Martensitic form diffusionless transformation when the asymptotic phase rapidly cools and carbon atoms do not get time to diffuse, resulting in the supersaturated body-centered tetragonal structure, okay, which is very hard and brittle. Next, which treatment process refines the grain size and improves the mechanical property compared to the casting? Okay, it is compared to the casting. What is the which one gives the much more refined grain size? Okay, and improves the mechanical properties. Okay, here he said that compared to casting, that is the crucial word here, because without if we do, there is no without comparison of casting. So mechanical properties, if we consider the hardness, we will get more in the quenching case. Okay, so in the case of casting and remaining heat treatment processes like annealing and normalizing, both cases we will see the formation of the paralytic phase only. So we should consider only these two things. And tempering is we use to surface hardening, but in internal structure will be uh, only mostly in the case of only getting the harder phase in the surface, like partially martensitic phase forming on the surface, and inside it will be the paralytic phase. For that it will be the tempering. So only options we left with the A and B. So in both cases, we will see the most improved properties with the normalizing, because we will have a finer microstructure, so we will have the good properties. Okay. So explanation: normalizing refers to the grain size due to faster cooling compared to the annealing, which produces the finer pell rate, improves the strength and toughness, commonly used in casting, forging to refine the structures. Okay. Next, a steel component is quenched in the water and develops the cracks. The most probable reason. Okay. So a steel component I am having and it is quenched in the water, produce the develops the cracks. So in if I do the cold working, we will see the how what is the internal stresses will be looks like is that. So on surface level, it will be the tensile stresses, and inside it will be the compressive stresses. In case of surface hardening, sorry, surface hardening case. Okay. So or if I do the cold working, entire microstructure will be filled with the compression and tensile stresses. Okay, not in a particular region, entire surface and it will be highly deformed. So those stresses uh, during the quenching time, okay, first let's see the options. So slower cooling, definitely not, because it quenching means itself faster cooling. Okay, residual stresses during the rapid cooling, yes, because residual stresses uh, will generates I mean that is the, and next is the formation of the paralytic phase. No, because in during the quenching phase it is a it will the formation of the martensitic phase we can see. And the grain growth is also not the reason, because in quenching there will be no grain growth, no to negligible grain growth. So rapid cooling during the quenching creates the thermal gradient, uh, so which volumetric expansion austentic phase to martensitic phase. Okay. So during the quenching time, because of the surface, at the surface level it is the much more faster cooling. So what happens is that when it is cooling, so first two few layers will be the reaches to the martensitic phase very rapidly. Then after nearby region, so here it will be the rapid cooling, but here the cooling happens only because of this conduction. So it will be much more slower compared to here surface region. So we will see the martensitic phase here, and here it will be the austenitic phase. So this big gradient martensitic phase, once it is forming, it will volumetric expansion will take place, that will generate the here tensile stresses, and inside the compressive stresses, that will that stresses may causes to crack. Okay. Next is the which microstructure expedites after normalizing ductile steel. Okay, which kind of microstructure we can see? So martensitic, no, it is during the quenching. Coarse perlite, it is during the annealing. Finer perlite, normalizing means finer perlite only. Bainitic, no, bainitic we will follow a totally different process. Isothermal holding, that is the different. So it will be the finer perlite. Okay. Next, the primary purpose of annealing is to, so increase the hardness, definitely not. It will not increase the hardness. Improve the wear resistance. This is also not. Reveal the internal stresses and increase the ductility. Yes, because it will reveals the internal stresses, because of the recrystallization will happen, and increase the ductility because of the grain growth and formation of the martensitic phase. No, definitely not. Okay, martensitic phase only forms during the quenching operation. Okay. Next, which are the following cooling rates arranged in the increasing order? Okay. So, which cooling rates in increasing order? So, quenching will be the much more faster cooling rate. Normalizing is the moderate, and annealing will be the slower cooling rate. So, answer will be the here annealing, normalizing, and quenching. Okay. So next coming to hardness in the steel primarily achieved by. So how we can so next we coming to the next chapter in this one. So that is the hardness. How we can get the hardness into the steel. So there is a multiple ways we can get the hardness into the in steel. First is the increase the carbon content. If we increase the carbon content, then hardness generally increases. Or if we increase the martensitic phase, that will also results in the hardness increasing. And if we decrease the microstructure, that is also increases the hardness. Or if you do alloying with the different elements, that may also increases the hardness. Okay. So heating below the eutectoid temperature, no, that is not the way. And formation of the martensitic by rapid cooling, yes, because martensitic is the one of the hardest phase, so we can easily get the and formation of the paralytic phase. Okay. And formation of the paralytic phase, no, and grain growth in the at the high temperature. So answer will be the formation of the martensitic phase by the rapid cooling. Hardenability of the steel refers to, okay. So hardenability is the ability to increase the hardness of the any material. Okay. So options will be A, maximum hardness attained, ability to resist the wear, and depth up to which martensitic form during the quenching operation, and resistance to plastic deformation. Okay. So ability to resist wear, once we have the hardness, then it will, we can say it is called as a able to resistance wear, but it will not cause the hardenability. Okay. Maximum hardness obtained, no. Oh, it is the hardenability we can define by this formula. Okay. So what is the depth we can retain this martensitic form, that will gives the it gives hardenability. Okay. And resistance to plastic deformation, that is also not, that is called as strength. Okay. Which of the following element increase the hardenability most effectively? Okay. So among them, carbon, sulfur, chromium, phosphate. Answer will be the chromium. Okay. Explanation: alloying elements like chromium, molybdenum, manganese, nickel shifts the TTT curve to the right. Okay. Delaying the paralytic benetic formation and allow martensitic formation at lower cooling rates. Okay. So carbon increases hardness, but not as significantly as the formation of the martensitic phase. Okay. So it is this kind of elements shift this TTT curve to the right side, so which makes the formation of the martensitic phase much more easier at the lower, even at the lower cooling rates. Okay. So next, standard test used to measure the hardenability is, okay. So which kind of test is that? Bernal test? No, this is the hardness test. Rockwell test? No, it is also hardness test. Charpy impact test? It is the to measure the toughness. So Jemmy quench test. So how this test is conducted is that, so we have a sample and we will heat it to above recrystallization temperature. Then we have a water jet coming and it will hit the sample. Okay. So after sample is completely cooled down, we will measure the hardness in vertically. Okay. So up to what height we will see the hardness retain will gives the hardenability of the material. Okay. Next, two steels having the identical carbon content but different hardenability. Okay. The steel with higher hardenability will so both are having the different carbon content, but one is the highest hardenability. Okay. So what could be the reason? Having the higher surface hardness? No. Forming the martensite at slower cooling rates, l- ha- having lower tensile strength, and having low carbon content. Okay. Answer will be the formation of the martensite at slower cooling rates. Okay. Higher hardenability means steel can form martensitic even at the slower cooling rate, even the oil quenching instead of water. Okay. Surface hardness depend mostly on the carbon content, not the hardenability. Okay. Hardenability only represents to the uh, formation of the martensitic phase. So if both are having the carbon content, that means one having the uh, can be formed martensite is easily. This can be due to maybe other elements like chromium, molybdenum, those may present in that alloy, so that it will shift the right steady curve to right. So martensitic form is much more easy in that alloy condition. Okay. Which factor does not significantly affect the hardenability? Okay, alloying element. Yes, alloying element affects the hardenability, and austenitic grain size. Yeah, grain size also will affect it, and carbon content and specimen shape and size. Okay, because shape and size also will affect, because if it is the bigger shape means so it will be take very long duration to cool. If it is the thinner sample, it can be much more hardenable. So carbon answer will be the carbon content. Reason, carbon increases the maximum hardness but limited effect on the depth of the hardening compared to the alloying elements and the grain size. Uh, Larger grain size increases the hardenability because it reduces the nucleation site for the perlite. Okay. Increasing austenitic grain size before quenching will be what could be the outcome? So decreases the hardenability. No, increases the hardenability. Yes, just as we discussed previously, larger grain size increases the hardenability because it reduce the nucleation site for the paralytic formation. Okay. So next, reduce the hardness. No, and prevent the martensitic formation. Okay. Coarser grains reduces the grain boundary area since the paralytic nucleates at grain boundaries and fewer nucleation sites delays the transformation. Okay. TT curve shifted to right and generates the greater the hardenability. Okay. Next, in the Jemmy test, hardness decreases with the distance from quenched end because carbon content decreases. No, cooling rate decreases. Yes, because here so we can see here. Here it is faster cooling because of the water quenching, but here cooling only happens due to conduction and due to the here air cooling. So that means here is the much more cooling rate is much more higher. Here cooling rate will be much more lower. So cooling rate graph will be looks like this way. So here cooling rate will be much more higher, and here cooling rate will be much more low. Okay. Okay. Next one. For the two steels, for the two steels with 0.4 percentage and 0.8 percentage of the carbon respectively. After complete martensitic transformation, what will be there? So 0.4 percentage of the carbon will be more harder, or 0.8 percent of the carbon will be more harder. Both will be same, or the hardness depend on the grain size. No. So hardness of the martensitic increases with the carbon content, because more carbon causes the greater lattice distortion in the body center tetragonal structure. Okay. So carbon content increases with will results in the higher hardness in the steel. Okay. So we can say hardness of the material with increases with the carbon content, and hardenability will be depends on the alloying element and grain size. If the grain size is high, hardenability high. Alloying elements, based on the alloying element, hardenability will also changes. Okay. Depth of the hardening will be dependent on the hardenability. If the hardenability high, depth of the hardness will be high, and maximum hardness will be depending on the carbon percentage. Okay. This is all about the hardness. Okay. So next, primary objective of the next we will come into the mass tampering and alternative tampering. What is it? Those are is that it is mostly the how we cooling it the material. So first option will be the increase the primary objective of the mass tampering is to increase the surface hardness, no, reduce the quenching stresses and distortion, and forms the magnetic phase, no, that is forms during the arch tampering, increase the carbon content. No, carbon content cannot be changed with the uh, way we do in the cooling. Okay. So reduce the quenching stresses. So how it is done is that, so it is arch tampering. I think I am not having it. Okay. I will draw here. So here is the C curve. It is the matricitic starting point and it is the matricitic end point. Okay. In case of mass tampering, we will cool up to here and we will hold for the some time isothermally. Then we will reach the martensitic phase region. Then we will leave it for the some duration. Then we will heat it to above martensitic starting temperature and we will hold it and cool it. Okay. So this is the mass tampering process. The mass tampering process, steel is quenched to the temperature just above the martensitic starting point, that is this one, and hold it to equalize temperature throughout the section. Okay, we will hold it. Why we have to hold it? Because if we have any component at surface level, it may forms the cool much faster compared to the inside level. So both to reach the uniform temperature level, we will hold it here for some time. Okay, then then before cooling to the room temperature, the minimal thermal gradient and reduce the internal stresses. Okay, distortion will be still forming the bottom state phase. Okay, so here so that if we it uniform stresses are uniform temperatures are reached, if we now cool it, the entire the region will be converted into the martensitic phase. Okay, so no need to so if we cool directly here, the because of the two different two cooling rates, the internal stresses may generate that we can avoid by this mass tempering process. Okay. Next, in mass tempering, the final microstructure obtained is martensitic phase, finer perlite, bainite, and tempered martensite. So it will be the bainitic phase because we are doing the isothermal holding and cooling. So here you can see in case of fast tempering, we will do cooling, holding, and we will again go to the this region and cooling and so once we reach here, it will forms the bainitic phase. Bainitic phase nothing but is similar to perlitic phase, but here the cementate Fe3C will form in a finer needle phase. Okay, there are two bainitic phases are there, upper bainitic and lower bainitic, based on the what is this height of the temperature we are holding it at. If it is the lower means it will be the lower bainitic phase, upper means upper bainitic phase. So how the bainitic phase will be look like? It will be look like it is the ferrite phase and it will be the cementite palette, cementite needles. Okay, here also cementite needles. It is for the upper bainitic phase. Suppose if I go for the finer bainitic phase, inside this ferrite place, we will see the needles of the Fe3C. Okay, outside also we will see Fe3C because there is no enough time to diffuse of this Fe3C out of the this alpha phase. Okay, here also we will see magnetic phase. Okay, the Ashtampering steel is quenched to temperature above the martensitic starting point, but within the bainitic transformation region. Okay, and held isothermally until the transformation complete. Okay, the final structure in bainitic which offers the good strength and toughness. Okay, yeah. Next, which of the following is a key difference between the mass tempering and ash tempering? Okay, what is the difference is that first both produce a martensitic phase? No, because in mass tempering you get the martensitic phase, in ash tempering you will get the bainitic phase. Okay, and mass tempering produce the bainitic phase? No, ash tempering involves isothermal transformation. Yes, we will hold it to isothermally, so it is there. And Martin's mass tempering avoids the quenching. No, that is also not the case. So it will be the mass tempering equalizes over the so uniform and entire component to reach the uniform temperature. We will do the mass temperature, so we will avoid the stresses. In mass tempering, isothermally hold it. So bainitic region until it to form the bainitic phase. Okay, so we are holding isothermally, so it will be the answer will be the C. Which heat treatment process produce the lower distortion compared to the conventional quenching? Okay, lower distortion. Okay, so which one it will be the full annealing, normalizing, mass tempering, and carburizing. Carburizing is a surface hardening process. Okay, So mass tempering we will use to, compared to the quenching, it will be mass tempering we will use to produce the reduce the internal stresses. So it will be the answer. The conventional quenching, the step temperatures gradually causes the residual stresses. Mass tempering reduces those gradient holding compared above the holding component above the mass tempering starting phase. So once it reaches the uniform temperature, then we will quench it. Okay. So here full annealing normalizing also produce a less distortion only. I think here question is bit options are bit wrong. Next, arch tempering is generally preferred over the quenching and tempering because it produces the higher hardness than the martensitic phase. So why it is that we can see here. So if we do the normal quenching, hardness difference how it is changing. But if I do the arch tempering, because of the benetic formation, impaired strength and elongation will be the properties are much more increases compared to the mass tempering and quenching. So that's why it is always referred to certain. So it produces the higher hardness martensitic phase. No, it eliminates the need for the tempering. Yes, because tempering be done to remove the provide the surface hardness and improves its internal toughness. Okay. So and to increase the carbon content, no, it forms the perlite. No, so it forms the Bennett. So option will be B. Eliminate the need for the tempering, because what are the we increase get the from tempering the toughness that we can achieve by this arch tempering process. Next, during the mass mass tempering, the steel quenched to the temperature below the martensitic starting phase, above the slightly above the martensitic starting phase, before the martensitic finish phase, above the eutectoid temperature and room temperature directly. So we have already seen here it is about slightly above the martensitic starting phase. Here we can see here we will hold it at the slightly above the martensitic starting phase. Okay. So which transformation is diffusion controlled? I think this is also we have seen. So martensitic transformation is the diffusion less transformation. Benetic, yes, here is also diffusion we are controlling isothermally. And shear transformation, no. A thermal transformation, no. So answer will be the Benetic phase. Compared to the martensitic and Benetic generally has. Compared to the martensite, Benetic generally has, which we have seen here. Here Benetic phase will give the higher impact strength. So that is nothing but a toughness is higher. Okay. So higher brittleness, no. That is a lower toughness, no. Higher toughness, better toughness, good strength, yes. And no particular use. No, answer will be the C. Better provide the both strength and toughness. Martensity phase harder but more brittle. So futures martensity phase has the and mass tempering produce the martensitic phase, harsh tempering produce the benetic phase. Isothermal holding in harsh tempering phase only. Oh. And here it's also called as a isothermal, but only for the very short duration, and distortions here in very low and here also low. Okay. And need for the tempering here no, and here because of it is a total martensitic phase, we have to do the tempering to increase its toughness. Okay. Toughness will be moderate and here will be very high. Okay. Next we will go to case hardening. So case hardening means we are increasing the hardness of the surface of any material. How we can do that is that, so there are one is that we can change the microstructure of the surface. So if we make it form the martensitic phase on the surface, that is that will increases the hardness. Or if we increases the carbon content in the surface, that is also increases its hardness. Or if we do the any other alloying element, then also its surface hardness will be increases. Okay. So case hardening, where we require the surface hardening. Okay, for example, gears, if we take, we require the gears surface to be very good wear resistance and high hardness. Okay, but inside we want the high toughness, because a same material we want a different properties at different locations. Okay. In that cases, we can go for the this case hardening process. Okay. So case hardening, uniform hardness throughout the section. No. Softer surface, harder core. No, because we want the harder surface, softer core. So answer, increase the ductility throughout. No, because we want the surface hardness and tougher core. So answer will be the C. Case hardening produce the hard wear resistant surfaces, while batensitic uh, by maintaining the tough and ductility core. Okay. Examples like gears, softs, and cams. Next, in carburizing, the increase in the surface hardness is mainly due to, so carburizing nothing but increasing the carbon content of the surface. So for in this case, we can do by three ways. One is the by solid form, we with charcoal and different material, and gas form, or in liquid form. So here you can see how the gas form we can make it is that if we supply the methane, propylene and gases, those will be react with the iron and produce the harder phase. Or liquid form, if we put this NaCl solution with a BaCl2, we can it will react with the iron and forms the FeC and BaCN2. And if we go for the solid phase, if it with the 80%, 85% of the charcoal and 50% of the BaCO, and we'll put in and some fly ash also, and we will reach to the temperature of 930 degrees centigrade. So that will make it surface harder. And nitrating also one of the process which we introduce the nitrogen into the surface to increase its hardness, that we will see later. Okay. So carburizing is the to increase the carbon content of the surface. This is the answer. So in carburizing, low carbon steel is heated in the carbon rich environment, and carbon diffused into the surface increases the carbon content. After quenching, high carbon martensitic forms on the surface gives the higher hardness. Okay. Which of the following case hardness process does not improve the carbon diffusion? So which hardness phase? Peak carburization Yes, the carbon content will be there, so it will diffuse. Gas corporation, pack corporation, nothing but a solid phase, and gas means gaseous phase, and liquid means liquid phase, as we seen just before. And nitrogen phase, it will be the we are introducing the nitrogen into it, so there the carbon diffusion will not be involved. Okay. Nitrogen is usually carried out at a temperatures yet with so above the austenitic temperature, below eutectoid temperature, at melting point about 1200 degrees. So nitrate we generally perform at the 500 to 550 degrees centigrade, that is the below austenitic range, hence there is no phase transformation occurs and quenching is not required. This result in minimum distortion. Okay. Which case hardening method produces the least distortion? So which one? It will be the peak corporization, gas corporization, cyaniding. Cyaniding means we are introducing both carbon and nitrogen and nitriding. So answer will be the nitriding. Why? Since nitriding does not require quenching and is done at the lower temperatures, it produces the less distortion compared to the carburizing methods. Okay. In carburizing case, we have to do quenching, so which will generate the stresses, internal stresses. So that we can avoid with the nitriding. So cyanide introduced into the surface. Carbon only, nitrogen only, carbon and nitrogen, and chromium. Answer will be the carbon and nitrogen both. So cyaniding is done in the molten cyanidic bath. Both carbon and nitrogen diffused into the surface forms the hard case. Okay. It is faster than the carburizing, but produces thinner case. Okay. The depth of the case in carburizing primarily depends on. Okay. It is depending on cooling rate, no. Holding time, yes, because the amount of the holding time is there, that much amount of the time the carbon can be diffuses. Okay. So answer will be the holding time. Alloying element, no, because it is the carbon only. So grain size, no. Carburizing is diffusion process in case depth following diffusion law, increasing the time and temperature, longer holding time equal to deeper casing. Okay. Which following steel is most suitable for the carburizing? So always the lower carbon steels, because higher carbon steel, it is already contain the high amount of the carbon, which makes it less diffused through it, and so which is the lowest carbon content that will have the highest uh, carburizing ability. Okay. Cast iron, no, cast iron are having higher carbon content, and stainless steel. So low carbon steel preferred because core remains the tough and surface carburization increases during the carburization, enable higher hardness after quenching. Which process form the harder alloy nitrates such as Al and CRN? So it is the nitrate, so it will be the nitrating. Carburizing only for the carbon elements, introducing the hardening, that is by carburizing and nitrating. Flame hardening also for the carburizing, introduction of the carbon only, so it will be the in nitrogen, in nitrating process. In nitrating, nitrogen reacts with the alloying element like aluminum and chromium, molybdenum forms the stable nitrates, significantly increases the surface hardness. Okay. So carburizing is for the carbon, cyaniding is for the carbon plus nitrogen, nitrogen is for the nitrogen, flame uh, flame surface hardening is the no diffusion. Okay. Quenching required in night except nitriding, everything will require the quenching. And distortion is because of the quenching is there, there will be the distortion. So in nitriding there will be no quenching, so there will be less distortion. And case depthing, how much deep we can get it is that in carburizing, we can get the very deep one because of the higher temperature and higher carbon content. And cyaniding shallow, nitriding also shallow, flame depending on the heat. So why we carburizing and flame both are similar processes. Only difference is that mm, carburizing we can do with the induction heating, but in flame we will use the mm, flames. Okay, so which we can use for the larger and irregular safe components, but in case of carburizing we can only use for the uniform safe ones only. Okay, next go to final thing, that is the uh, heat treatment in the non non ferrous materials. Okay, why we have to do the heat treatment for the non ferrous materials is that to get the chemical homogeneity, because and to in case of aluminum and copper alloys we can do get the precipitation strengthening. And to these are the major reasons, and to change it to microstructure. Okay. And to reduce the any residual stresses because of the cold working, those also we can achieve. Okay, so how we can so edge hardening, precipitation hardening is most effective in the alloys that. So what is the precipitation hardening first? So in precipitation hardening happens when the alloy, if I am having an alloy here, it is the two alloys, two elements are there, both will be soluble here. Okay, but once it is cooling down, one alloy it will become super saturated, one alloy, so that will become precipitate out. Okay, some phase will be precipitate out. Okay, in a metal matrix. Okay, that precipitated out will be act as a as we have seen here, barrier for the dislocation to move, so that makes it much more strength, mechanical properties will be increases. Okay, age hardening, precipitation hardening is most effective in the alloys. Okay, slow shows complete solid solubility. If complete solid solubility is there, then there is no supersaturation and no precipitation. So that is not the answer. So no solid solubility, then also it is not, so then it will be totally segregated out. So shows the decrease in solid solubility with decrease in the temperature. Yes, that is the case where it will be formed. Contain the no alloying element. Then if it is the pure phase means there will be no transfer, no precipitation formation. So it will be, the answer will be the C. Next, the correct sequence in the precipitation hardening is, okay. So what is the correct sequence? First is the solution treatment, then quenching, then aging. Okay. So first we will do the solution treatment, that is heating to the dissolving alloying elements, then quenching, rapid cooling so that supersaturated solution will be formed, so nucleation will form, then aging, control heating allowed to finer precipitate to form. Okay. Next, which of the following alloys are best known for the precipitation hardening? Okay, pure copper. No, if it is a pure copper means there is no supersaturation. Brass, no, brass will not be formed. Duralium, that is nothing but copper and aluminum combined alloy. Yeah, here it will be formed the super precipitations. And cast iron, no, cast iron also not. So next, natural aging occurs at which temperature? At higher temperature furnace, at room temperature. Natural aging means it will be the and below 0 degrees during the solution treatment. After quenching, some alloys like aluminum, copper undergo precipitation at room temperatures over time. Okay. This is called the natural aging. Artificial aging done at the elevated temperature. It is natural aging is the much more slower phase compared to the artificial aging. So increase the aging speed, so we can do the bit at elevated temperatures. We can hold it to, so the precipitation formation will be increases. Next, over aging in precipitation hardening leads to. So if the overaging is more than the precipitations will be become coarser. So if it is the coarser, then it will not act as that much so obstacle for the this dislocations. Instead of those will be slip through the this precipitations. Okay, it will go bypasses it. Okay. The spacing increases, the coarser particles are less effective in blocking the dislocations, and strength and hardness will be decreases. Okay. Next, which of the following non-ferrous alloy that cannot be strengthened by the precipitation hardening? So that is the brass, because brass does not show the required solubility variation with the temperature needed for the precipitation hardening. This is mainly strengthened by the cold working. Okay. Next, the strengthening mechanism in a precipitation hardening is mainly due to because grain growth, no, solid solution softening, no, obstacle to dislocation motion by the finer precipitates, yes, as we seen before, and martensitic transformation. No, there is no martensitic formation. Okay. Next, in age hardening, aluminum alloys quenches after solution treatment is necessary. Form perlite, form bayonet, retain the solute atoms in a supersaturated solution, increase the grain size. Perlite and bayonet only forms in the iron alloys and retards supersaturation formation. That is the reason why we do the uh, quenching in case of aluminum alloys. Increase the grain size? No. So rapid cooling prevents the diffusion and precipitations during the cooling, prevent the supersaturation solid solution required for the subsequent aging. Okay. Which of the following alloys commonly precipitation hardening in aerospace application? This is the aluminum, zinc, and magnesium alloys. That is the 7000 series of aluminum alloys. Okay. Due to its high strength obtained at precipitation hardening. Okay. So in annealing, we can use for the most of the materials edge hardening, that is only for the aluminum, magnesium, and nickel alloys, and cold working for the copper and brass. Okay, key requirement: recovery, recrystallization, solubility with increases the temperature, and plastic deformation. Okay, grain refinement, fine respiration, and dislocation density increases. This is the